I'm Daphné Trama. I'm a PhD student and I work at CEA in Palaiseau near Paris in France. And my PhD focuses on homomorphic transciphering. And I guess it's all you have to know. But I'm very glad to present to you today a joint work with my colleagues, Pierre-Emmanuel, Aymen, Renaud, and Nicolas. So I know this is an FHE.org meeting, so I believe you are all already familiar with homomorphic encryption. I would like to start the presentation with a quick reminder on FHE, just in case there are any FHE beginners among us. So FHE stands for fully homomorphic encryption, and it allows computation over encrypted data, particularly for two encrypted messages M1 and M2. We expect that the sum of the encryption would give an encryption of the sum of the two values, and we would like also that the multiplication of the encryption of two values will give the encryption of the multiplication of the two values. And note that if M1 and M2 are binary values, the relation can be translated with logical gates. Finally, homomorphic encryption security relies on the LWE problem. So that means that we add noise to our messages, and we need to be able to reduce or refresh the noise of the ciphertext. Otherwise, this can lead to incorrect decryption. Okay, so the key idea behind homomorphic encryption is to be able to compute any computation. And in the early years of FHE, the hope was to achieve this goal by executing Boolean circuits over binary ciphertext. And this had several advantages. For instance, the size of the parameters that are small enough to allow fast and efficient computation of logical gates. And although this approach is universal, it also leads to some efficiency bottleneck, especially due to the circuit expansion when trying to perform operation over ZT. For instance, this is the circuit for an 8-bit adder, and you can see that it's way more complex than just 8 times a 2-bit adder. So, to circumvent this efficiency bottleneck, we decided to work with another approach, that is to say, the use of TFHE programmable bootstrapping in integer mode. So to explain this approach to you, I'm afraid that I have no choice but to bore you with some theoretical background, but I'll try to keep it short. So, TFHE is a fully homomorphic encryption scheme. It was introduced in 2016 and is implemented under several libraries. And for our work, we used the C++ TFHE lib library. So, in a nutshell, TFHE works with a finite space of plain text of size p, and we call this space p. And it sends the elements of this space into the discretized storage on as many values. And I would like to draw your attention to the fact that the size of the plaintext domain is small, and it's one of TFHE's limitations. Then TFHE proposes three structures to encrypt messages, but here I've only put the simplest one. And in fact, you don't need to, sorry, I'm panicking. Okay, so this is the simplest one, and the other two are hidden in bootstrapping. But to understand this presentation, in fact, you only have to know that you can encrypt either a single value of your plaintext space p or polynomials that have coefficients in p. Okay, of course, you also have to understand bootstrapping. So bootstrapping is a procedure that allows to reduce the noise of a ciphertext. And with TFHE, it relies on three basic operations that I present here. The first one is the blind rotation, which rotates a clear text polynomial by an encrypted index while reducing, and it returns the encrypted polynomial. That's why it's in green here. And then you have the TLWE sample extract that extracts a coefficient from an encrypted polynomial and converts it into a TLWE sample. And finally, you have the key switch that allows the switching of keys and parameters. And for instance, here, we use it to go back to the initial blue key. Okay, but in fact, we can see bootstrapping as an indirection from a clear text value table with an encrypted index while reducing the noise. So that means that we can put whatever we want in the table. So why not the values of the function that we want to evaluate? For instance, we have a function f and we have the corresponding lookup table. Then we just have to replace the coefficient of the polynomial to be rotated with the one of the lookup table of f, just like this. And then we can proceed to the bootstrapping, and at the end we obtain an encryption not of m, but of f of m, and without any additional cost. This method is called programmable or functional bootstrapping, and we used it to implement more than 40 instructions. But a lot of these instructions are bivariate instructions. That means that they have to take several inputs. And to do so with homomorphic encryption, we had to find a bootstrapping method that allows bootstrapping on several encrypted inputs. And that's why we decided to work with the tree-based method. So I believe that there is nothing best as an example to give you a hint on how it works. So let's say that we take the message base B corresponding to 2-bit messages, and we have two messages, M1 equals 1 and M2 equals 2, and there are corresponding ciphertexts C1 and C2. Now, we want to compute the addition of the two ciphertexts. So the first thing to do is to compute the lookup table corresponding to such operation. And I've put this here. It's a very simple table. Once this is done, we can decompose this lookup table into 4 polynomials, P0, P1, P2, and P3. And then we will perform bootstrapping on each one of these polynomials with selector C1, which encrypts 1. It will give us 4 new encryptions that we can put together to create a new polynomial that will be rotating during bootstrapping, this time with selector C2, that encrypts 2. And this will give us an encryption of 3, which is what we wanted. So this is a tree-based method. And we also used multi-value bootstrapping, which is an optimization that allows the factorization of blind rotations. As the blind rotation is the most expensive operation of the bootstrapping, it's really great for TFHE efficiency, and of course we used it. So the idea is, for instance, here to factorize the blind rotate in the first layer of the tree, and with one blind rotate we get all the 4 ciphertexts. But in exchange we have to compute clear text ciphertext polynomial multiplications. These multiplications are cheaper than blind rotate, but they have an impact on parameters. Okay, so I believe this is it for the TFHE toolbox. Now we can go into the details of our approach. So we decided to work with 8-bit values. That means values that are taken between 0 and 255. But secure parameters for such a plain text are very large and do not allow efficient bootstrapping. And to be honest, my computer almost crashed when I tried to generate the keys. So we had to find a solution, and in fact there is a simple solution to it. It is to break down our age data into a smaller decomposition basis. And from 8-bit messages, there are several possible decompositions. So the first one is to decompose our 8-bit message into 2 4-bit messages, or 2 nibble, because nibble is the cute name for 4-bit entities. And this corresponds to 2 digits in basis 16. Or we can decompose our message into 3 basis 8 digits, but with the most significant digit only on 2 bits. Finally, we can also decompose our message into 4 bases, 4 digits, like this. But note that the smaller the decomposition basis, the smaller the parameters, and thus the smaller the bootstrapping evaluation. But on the other hand, the smaller the decomposition basis, the greater the number of digits in the decomposition, and thus the greater the number of bootstrapping to be evaluated. Therefore, a trade-off must be found between the parameter size and the number of bootstrappings to be performed. And spoiler alert, we found that basis 16 is the optimal basis for this kind of work. So let's see how we found that it was basis 16. So to find which basis was optimal, we decided to evaluate the execution timing of several building blocks. Of course, one of them is the classical bootstrapping, but as our approach relies heavily on tree-based evaluation, we of course also assess execution timing of a tree-based method in all the possible decomposition bases. So we called our tree-based method evaluation implementation LUT-eval. And as you can see here, LUT-eval takes as input the equivalent of an 8-bit message encryption. That is to say, here it takes 2 basis 16 digits, here 3 basis 8 digits, and so on. And you see that the number of digits of the decomposition have an influence on the number of branches that are in fact bootstrapping, but also the depth of the tree. Here we have only 2 layers, here 3 layers, and here 4 layers. Note that even if LUT-eval takes as input the equivalent of a 8-bit message, it only returns the encryption of a basis bit digit. So we also wanted to evaluate what we call LUT-eval. LUT-eval is used to factorize the code to LUT-eval. In fact, when you want to evaluate several lookup tables but on the same input, you can call LUT-eval. Instead of doing, for instance, here in basis 16, 2 call to LUT-eval side by side, we prefer to factorize the first layer of the trees and then to proceed normally to obtain our 2 digits. So I hope this is clear enough for the building blocks. If not, maybe this table will help you understand. So at the left of the screen, you have 4 building blocks per decomposition basis. Of course, the classical bootstrapping that we called simple boot, but also our LUT-eval tool and 2 flavors of the LUT-eval tool. So LUT-eval star is the factorization of the evaluation of 2 lookup tables, as seen here for basis 16. And LUT-eval square is the factorization of the evaluation of 4 different lookup tables on the same encrypted inputs. So you can see that, of course, the number of output digits correspond to the number of tables to be evaluated, whatever the basis. Okay, but it's important to note that the amount of information being computed is not the same. For instance, with basis 16, when we evaluate 4 lookup tables, it gives us 4 basis 16 encryption. That is the equivalent of 2 basis 256 encryption. But when you compute exactly the same thing with basis 4, you also get 4 output digits, but basis 4 digits. That is the equivalent of only 1 basis 256 encryption. Okay, and then I've put NBR, that is the number of blind rotation to be performed, and also NKS, which is the number of TLWE to TRLWE key switch. That is to say, the operation that we do when we obtain here the TLWE ciphertext and we pack them into one TRLWE. And of course, we have the execution timing of all these operations. I believe it's a surprise for absolutely no one that the classical bootstrapping is the fastest for basis 4. But as said previously, in fact, our approach relies more on tree-based method. So it's interesting to look at evaluation timing of LUT-eval and MV-LUT-eval. And it is clear that for this type of building blocks, basis 16 is the optimal one. And even more, when looking at the same amount of information to be computed, for instance, to obtain one full 8-bit encryption, for basis 16, it only takes 0.23 seconds. For basis 8, it's at least 0.93 seconds, and in basis 4, it's almost 2 seconds. So that's why we decided to work with basis 16. And using all these building blocks, and mainly LUT-eval and MV-LUT-eval, we were able to implement a set of 40 to 50 instructions that we can categorize in 4 categories. For instance, we have arithmetic instruction with addition, subtraction, multiplication, division, modulo. Also bitwise instruction, so and, or, and so on, but also shifts and rotations. Also comparisons and other instructions such as minimum, maximum, conditional affectation, absolute value, and so on. So if you're asking yourself, what is this notation? For instance, for add, we have 2 versions of the operator. We have add that computes homomorphically the addition of 2 encrypted bytes, but also add I, which computes the addition of 2 bytes, one of them being encrypted and the other being a plain text value. And it goes the same for all the operators that you see here. Okay, so I'm not asking you to take my word for it when I say that we've implemented all of this operation. Of course, that would be too easy. So I will explain you how we did it. But first, maybe some notation that will ease the end of the presentation. So for a message M, we denote with brackets the set of its valid encryption. And when we are talking about 8-bit values and their corresponding ciphertext, we use uppercase letters. And when we are talking about nibble and their encryption, we use lowercase letter. So when working with basis 16, we have, for instance, a plain text value M, and we want to decompose it into 2 nibbles that we call M0 and M1 that satisfy this decomposition equation. And then to encrypt M, we only have to encrypt M0 and M1 separately, but using the same key to obtain the global encryption of M. Okay, so now very simple operator. Let's say we want to compute the logical AND instruction on 2 8-bit ciphertexts that are called C and C prime. That is to say, we want to obtain C bar encrypting the logical AND of H and H prime and the logical AND of L and L prime. Well, the first thing to do is to compute the table, the look table of the function that we want to implement. In this case, it's a very simple table corresponding to the logical AND. And once that we have this table, we just can call our LUT-eval tool to obtain C0 bar and C1 bar. So the first one is obtained with the encryption of the most significant nibbles, and the second one with the encryption of the least significant nibble. And that's it. We've computed the logical AND of 2 8-bit ciphertexts with only 2 calls to LUT-eval. Okay, so I propose we go on to something a bit more challenging. For instance, let's find a way to implement any univariate function. That is to say, for a certain function f that takes as input an 8-bit value and return another 8-bit value, we want to be able to compute it homomorphically. So let's call tab the 256 element table that correspond to the lookup table of the function f. The first thing to do is to create from this table two tables. The first one will compute the most significant nibble, MSN, part of f of I. And the second one will compute the least significant nibble, LSN, part of f of I, with I taking all values between 0 and 255. And then, well, you know what to do. You have to call LUTs to obtain C bar, encrypting the right value. That is to say, you can obtain C bar with these two calls to LUTs. So you can see that the two calls to LUTs takes a different table, but the encrypted inputs are the same. That means that we can factorize bootstrapping and obtain the same result with a single call to LUTs. And in fact, we have found a way to compute any univariate function. Okay, so now what about bivariate operations? So there are operations that take two inputs. For instance, it's the case of the addition. So let's say that we want to homomorphically compute the addition of two ciphertexts C and C prime. That is to say, we want to compute C bar, such that C bar is the encryption of 16H plus L plus 16H prime plus L prime modulo 256. So why modulo 256? It's because we want a result on 8 bits. So as for the univariate operation, the first thing is to compute the table that we will use. So for the addition, it's a bit more subtle than for the AND, for instance, because when you add two nibble, maybe there will be a carry that will be created. And this carry must be taken into account in the homomorphic computation. So we need two tables. The first one will give the result of the addition of two nibble modulo 16, so we have a result on 4 bits. And the other table, tab carry, will give us the carry that was created during the addition of the two nibbles. Okay, so using these two tables, how do we compute the addition? Well, first, we will manage with the least significant nibble, the encryption of the least significant nibble. We will add them and compute the carry. Then we can manage the encryption of most significant nibble and just add them together. And of course, we don't forget to propagate the carry by additioning this result and the one giving the carry. And then C0 bar and C1 bar compose our encryption of the addition of C and C prime. But in some cases, the user knows that at least one of the encryption C or C prime is an encryption of 0. And what happened in this case is that we know that absolutely no carry will be created. So we can optimize the addition operator in this specific case. That's why we created the add Z instruction that is computed as follows. As we know that there will be no carry, we just have to make two calls to LUTs with tab add. Okay. And in fact, you see how it can be easy, but for other instructions can be a bit more complex. But it allows to do a very large set of instructions. So I've put here all the instructions that we were able to implement with this method. So you can see that only a few of them take more than a second to be executed. It's the case of the division or the modulo, but in most cases, the execution of our instruction takes less than half a second. So it's nice. And as it's a very exhaustive instruction set, we can use it to implement almost any algorithm. So I propose we look at some together. For instance, you can compute a bubble sort of an array of encrypted values. And to compute the swap, of course, you can either compute the max and the mean and then swap, but we found that this method is more efficient. So first, you have to obtain the result of the comparison of A of j and A of j plus 1. So if A of j encrypts a value that is superior to A of j plus 1, CB will be an encryption of 1. Then you can use the conditional affectation, which returns CB times A of j. So if A of j is indeed greater than A of j plus 1, this instruction will return A of j. And you see that we have the opposite operation that returns 1 minus CB times what you put in second input. And you agree with me that only one of these two operations will return a ciphertext encrypting a value that is not 0. This is why we can use add z here. Then we do the same for the other element in the table, and this computes the swap. But there are maybe easier algorithms to compute. For instance, the maximum, or where it's really the same algorithm as in plain text domain, but you just have to use the homomorphic operator instead of the plain text one. And the same goes for a square sum algorithm, when you can do the multiplication and addition, put them into an accumulator, and then return the accumulator. Okay. But in fact, you can also do way more complex evaluations. For instance, let's take the sigmoid. I believe you all know the sigmoid. It's often used as an activation function for neural networks, for instance. Well, we decided to do a precise evaluation of the sigmoid. So what do I mean by precise? Well, we decided to work with signed fixed point arithmetic messages on 16 bits. With 8 bits for the integer part and 8 bits for the decimal part. Then a message n can be decomposed under nibble decomposition like this. And of course, the encryption of m is just the encryption of each nibble of its decomposition. So how do we homomorphically evaluate a sigmoid on such inputs? Well, let's first look at how would we do it on the plain text domain. Of course, we have to discretize it to be able to compute local tables. But once this is done, we can compute what we call here sigma tilde, with I the integer part of the input and j the decimal part of the input. As you can see, the result integer part is in fact a Boolean value that is a result of this condition. As for the decimal part, it's the evaluation of the ith lookup table depending on I, and of course taking as input j, with our table corresponding to this. So in the homomorphic domain, we really just translate the evaluation of the sigma tilde in the homomorphic domain. So you see that to obtain the integer part, we really do what I said, that is to say, a greater than a homomorphic comparison with a clear text value. And then to obtain the decimal part, we have to do several computations and then use the XOR or add the operation to obtain the final decimal part. I propose to take an example to help you understand. Let's say we have a message n that is equal to 0.25. That decomposition is this one. That means that the encryption of this message is C, with C0, C1, and C3 encrypting 0 and C2 encrypting 4. So we begin with the integer part result. So we do the homomorphic comparison. We know that C0, C1 encrypts 0, and 0 is smaller than 6, so it will return an encryption of 0. For the decimal part, for I in this range, we have to compute what I call here CTI. That is, in fact, just the evaluation of our tree-based method on the I table and taking as input, well, the decimal part of the ciphertext. We also compute CBI, which is just a test to see if C0, C1 is an encryption of I. And finally, we can compute the conditional affectation. And of course, this test will be different from 0 only if only if I equals to 0, because C0, C1 is an encryption of 0. That means that the only value here that will not be 0 is C0 prime. And when we do the addition of all of this, it will return C0 prime. So we have computed a very precise sigmoid. Okay, I hope you're still with me. Just let's resume this algorithm. So I've put here all the algorithm we talked about. I've also added the average. When we have a table of, for instance, 5 values, we all add them together. They are 8-bit encrypted values. But when we do the division, we do the decimal division. So the final result of average is a 16-bit output, just as we've seen for the sigmoid. And with the sigmoid that I've just shown you, we've implemented a full neuron. That means that we also implemented addition and multiplication for assigned point fixed arithmetic inputs. And you see that when running over every side instead of sigmoid, the execution is at least 2 times faster. So yeah, this execution timing seems nice, but maybe we should compare ourselves to some state-of-the-art to be sure that it's actually nice. So that's what we did. We compared ourselves with the recent Juliet, that is a general purpose homomorphic computation framework, but working over binary ciphertext. And we also compared our approach with FHE compilers that are the E3 framework, Cingulata, and Concrete. And we compared it on the benchmark of algorithm that we had. And you see that when the Boolean circuit corresponding to the algorithm is small, then it seems that the binary approach may be a little bit more efficient. But when we have the expansion of the circuit that is very important, then our work is the best option. And as Cingulata is our our bigger competitor, we did a deeper comparison with it, where we also take a representative set of instructions and compare our execution timing with those of Cingulata. And you see that for the division, we are way faster than Cingulata. For the addition, we have similar execution timing. And for the multiplication, again, we are faster. But it seems that Cingulata is really unbeatable for the ciphertext selection. And we've also put here again the algorithm, but what's new is that you have the number of blind rotation and key switches, and the number of blind rotation for Cingulata, in fact, corresponds to the number of gates in the Boolean circuit. And you see that when this number of gates became very large, then our approach is the most efficient one, even when it's on simple instructions and not algorithm. So this is the conclusion of this work. Maybe I will leave you with some key takeaways. So I've presented 2 generic tools to implement any operation, and we call them Anvil, Duval, and Noteval. And using this tool, we were able to implement a large set of instructions, including division and modulo, minimum and maximum, but also more classical operations like addition or multiplication. And what is not fully emphasized in this presentation, but there are more details about it in our paper, is that it works for other types of ciphertext too. For instance, unsigned messages, and as we've seen, fixed point arithmetic messages. So I advise you to see our paper if you're interested. And as a matter of perspective, yeah, it would be very interesting for us to look at work on advanced software optimization or hardware implementation to even boost our implementation, and also to investigate several values for the bootstrapping error probability to consider the recent CPAD attacks. So that's it for me. Thank you all of you for coming, and I would be happy to answer any question you may have.